much. My name is Paul Downen, and I'm here to tell you a little bit something about coinduction. So in contrast from something we all know, is induction is an insanely useful tool. We use it all the time, all over in programming languages and just programming itself. And it's the kind of main workhorse. But sometimes you need something more, right? So lots of programs will interact with the outside world, take inputs and outputs while they run. Right? This is kind of co-inductive in nature, and there's lots and lots of examples of this. You can kind of think of a web server or operating system are classic examples. And it also comes up sometimes when we study the semantics of languages, right? So we reason sometimes about by simulation and dealing with infinite processes, or when you want to reason about some kinds of effect systems, there's different techniques that use that. So I mean, idealistically, I should just be able to use coinduction the way I sit down and write a paper for JFP or ICFP or one of these conferences, and I do a proof by induction. So let's just do a coinduction. I mean, what's so hard about doing coinduction anyway? It should not be a big deal. So here's a super basic hello world for coinduction, right? So I've got infinite streams where there's always more elements in the stream, and each stream has a head and tail, right? So head is the first element, the tail is the rest. And here's just a super simple mapping function that, given a function, we're going to apply it to all of the elements in a stream. And we want to know that if I map the identity function, which does nothing, on a stream, I get back the same stream. So how do we prove this? Well, one way might be general coinduction, right? So we say by coinduction on the stream, and so we assume the coinductive hypothesis that mapping the identity over x's is x's. And well, this is a really simple proof, right? I mean, there it is. That's what I had to prove. So I'm done. QED, easy, right? So you all believe me, of course. But maybe something feels wrong about this. I mean, I should probably say something about map, or I'm not really doing anything. So this feels wrong, and it is wrong. So I should probably do something, right? So I should maybe inline the definition of map and then do a bit of calculation and show that I wound up where I started again. OK, now this feels a bit more like a proof. And what's different this time? I mean, technically everything I did before was correct, quote unquote, but obviously it's not a real proof. And what's different this time, and it's kind of the typical sort of technique, is OK, I use the coinductive hypothesis only in a productive context or a guarded context, right? So I've only used it in the context in which I've applied a constructor. Right, and this is a typical kind of restriction that we will use of, OK, the coinductive hypothesis is a little bit much. You can only use it sometimes. All right, so if that's the case, then hey, maybe here's another theorem. So the other one was a bit of an easy warm-up because it's obviously true. Here's another one, which would be very adventurous, that the stream which starts with 0 and then is always 1s is equal to the stream which is always 0. And it'd be very interesting if this theorem was true, because then 1 is equal to 0, and we're getting a very interesting mathematics if that's the case. So clearly something would have to happen here. And well, here we go. Here's a little bit of rewriting. You don't have to look too closely at all of it, but the idea is every line technically is correct, but obviously something must be wrong. And it's not really guarded in the sense, I mean, I've only used the coinductive hypothesis in the argument of a constructor, so it's kind of guarded. But something else obviously must be going wrong, and it's because, OK, even though it's kind of like in a guarded context, it's not guarded anymore, because I've used tail. That's just actually the thing that's gone wrong. So it kind of looked like it may have been productive, but in actuality it wasn't, because of this like extra semantic content that is needed to actually tell if it's really guarded. So it's not purely as naively syntactic, or it's a little bit more nuanced than you might have thought. And this is like the problem with this whole enterprise, right, is that fundamentally the coinductive hypothesis done this way is way too powerful, and it makes it too easy to create vicious cycles, so we have to restrict it to good contexts. And the problem is the division between good and bad context has this tricky semantic content about what somehow the meaning of these things are. And I kind of started in a very particular style of proof, which is a certain shape where we're doing a set of calculations. And you can kind of do it if this is your shape, but good luck if your proof is actually a few paragraphs of English prose, of analyzing English and understanding what is a good context there. I don't actually know how to help you. But even in the setting, right, where we've got a particular shape of proof, proof assistants can help us, right? They can do some of these checks and they get it correct. That helps. But the experience is maybe not exactly what you want. And so let's look at kind of what that looks like. So here's a formalization of just these ideas, right, in a system like Rock. So we can define a coinductive type for streams. I can define the mapping function. And, well, we can't exactly prove that they're equal in the most simplistic definitional sense, but we can prove they're kind of like equivalent in the heads and the tails, right? So this is how we get going. And here's two proofs, and they're honest proofs in the sense that I'm not trying to cheat and do something silly like I did on the very first example, right? I'm actually analyzing it and going through. But there's a subtle change, which I'll leave you to puzzle out what the actual difference is. And if you write this into Rock and you start stepping through, it nods along and says, yes, there's no problem, everything's great. And you say, oh, OK, so there's no goals left. I proved my theorem, and then I hit QED. And on the right, it says, no problem, you're good. And on the left, it says, actually, no, you were wrong all along. And the only hit you have is you can try to print out the proof term that was generated. And in small examples, this is really hard. And in larger examples, it's essentially impossible. Try to figure out what happened. And I don't know. That's not what I wanted, right? This is not what I was trying to do. In the beginning, I was even just trying to sit down and on paper write a proof and know what made sense. And the issue is that when I do proofs by induction, there's kind of built in the guardrails, right? I assume in the inductive set that it's true on some n, and then I prove it on the next number. And I don't have the safety rule for coinduction. So what I actually want is a formalization or a formulation of coinduction where I have knowledge when I apply the coinductive hypothesis that it will actually work and not have a problem without some sort of secondary syntactic check that I don't always have on pencil and paper. So let's look at another way, another kind of style of doing coinduction where we can do it with confidence without this second elaborate check. And the kind of idea where this comes from is the idea of copatterns, right? So this has been around for quite a while in a system like AGDA. And if you're not familiar with it, that's OK. If you are, the point is that more of the structure is there, and there's less hidden from you, and it gives you kind of naturally the right way to think about these things. And so let's look at what we all know, what's all familiar, and what doesn't have any problems is induction on the natural numbers. So the shape of this is to prove that a property holds on all of the numbers. We have to prove that it holds on 0. And then the inductive step is if it holds on n, it holds on n plus 1. So how do I do something with exactly this shape, but for coinduction? The trick is I don't
Sorry,
Yes.
the mic is on.
Ah. Maybe, is it, oh, this is way better. Okay, let me hold it back there. Is that a good volume? Okay, perfect. Yes. So we kind of calculate through, and the thing to notice here is all of that kind of fudging around about guarded contexts, we can throw it out the window because the guard is the marker H from the coinductive hypothesis, and the rewrite happens, right? So the kind of normal proof still goes through, but we don't need a secondary check. And that means we immediately get feedback when we try to do this for the broken proof that should never work, right? So somehow this kind of bait and switch that if I start with a 0 and then become all 1s, that's not the same thing as always a 0 forever. And let's see what goes wrong. So the head case does work because they both start with 0, so that's not where the problem is. The problem will be when we try to work out the tail. And before, when I tried to trick you, I kind of snuck in a little bit of distraction by expanding and then trying to apply the coinductive hypothesis too far in. But now it actually just does not match. This does not match the coinductive hypothesis at all. Not because of some weird productivity thing or secondary check. Literally, this does not match the left-hand side because the H is too far from the thing I really wanted to rewrite. It's just not a match. And if I tried to go the other way and trick in some other way, well, I could get started. I can apply the coinductive hypothesis, but then I can never reach the other goal on the other side. So there's no way to make any progress towards bridging the gap. And it's not due to productivity. It's not due to some syntactic check. It's just the structure of the coinductive hypothesis. So this is kind of the main informal idea. But how do we make this formal? How do we make it a particular actual system and come up with axioms that capture those ideas? And the trick is to use, rather than intuitionistic logic, a form of classical logic. And the reason is we need to give equal status to not just answers, but also questions. So we have both questions and answers we can ask at any particular type. And so a producer of a type A gives an answer that somehow corresponds to that type, and a question of that type asks a question, or a consumer of a type asks a question. And so the fundamental unit of computing is when you stick these two things together, right? This is the long ago familiar rule of merging answers with questions. And so if we start with the easy thing we already know, right? There's a few ways we could express regular primitive induction on numbers, the thing we are very familiar with. So a property is true if it works on any value. So what are all the values? Well, it could be 0 or y plus 1. And so the rule of induction is saying, well, if I've got maybe some unknown x in my context, I can work out some result by just handling these two cases. And in the inductive step, we have to work it out for any generic number, and all we know is that the property already works on it. Then we work on it in the n plus 1 case. Of course, we can summarize this as a closed axiom, which is sound and doesn't break our logic, right? We can just use this whenever. So the same thing, we can do that for streams as long as we can talk about observations, right? And so observations here, they take streams as input. And now they only have two cases. Like the only two observations I can make on a stream is I ask for the head first, then I pass that to some observation wanting the A, or I can ask for the tail, and I pass it to some other observation on streams as well. And so here now, instead of saying I've got some unknown x, I've got an unknown observation that somehow processes streams. And we have the two cases, the head case and the tail case. And in the tail case, we have to say this works for any arbitrary stream observation, where all I know is that the property is established for it already. And this, unlike the usual coinductive general kind of fixed point form, gives us an axiom for coinduction, which is closed and is sound and doesn't break our logic. So this restricts, or this lifts the kind of restriction we normally have to impose, that we have to check these things and make sure that they're used very carefully. We've actually got a sound reasoning principle that works. And just as a sort of quick example, I mean, streams are the typical simple example to get going, but they're kind of boring, right? This generalizes to all sorts of other principles as well, just by following the structure, right? So you could have, instead of infinite streams, infinite binary trees, right? They're kind of rivers that fork, and then I can go down either the left or the right path, and we can get sound principles for other structures like that too, just by following the shape. Okay, So that's kind of the general informal idea, something you can just do on pencil and paper without thinking too hard, and the main trick of formalizing these rules for reason about equality. But I don't know about you. Sometimes I like to compute things, and I want to know that my proofs about computation actually work. And so the minimum requirement is that if I say things are equal, then they should actually be equal in some sense about computation, which is typically contextual equivalence, right? So if I claim, the rules of my system claim that two programs should be equal, then if I actually run them in some arbitrary context, I should always get the same result. And this is kind of one of the main results in the paper. And the proof of how this is done is based on a particular type of logical relation using orthogonality. And because we've got these recursive types, we need to figure out the fixed points of coinduction and induction in some sort of subtyping lattice. And the main kind of key trick to make this work is that there's two ways to define recursion, two different ways to solve the fixed point, and they happen to coincide, which usually is trivial and is not quite so easy in this case. And this is interesting because, of course, as a corollary, the main one is that true should not be equal to false, which we extract from contextual equivalence, or that if I say that I've got two programs that all they can do is emit a Boolean answer on alpha, then if they're equal, either they both send a true to alpha or they both send a false to alpha and not something else. What about if my program has effects? And in classical logic, we kind of already have one baked in. So we need to be able to handle the case if there's something more interesting, like an effect happening. And I'll kind of mention that in this sort of setting, there's actually a maybe surprising wrinkle we normally don't think about, but there's information effects. If we erase or duplicate information, this has exactly the same sort of problem in the opposite way for certain other cases. So we have to think about that too. In certain cases with certain effects and certain orders of doing things, you can have inconsistency, so you have to be careful. But in reality, it's the exact same thing we've already known since forever, since dealing with any language with evaluation order and effects. So there's actually nothing new here, but we do have to do it correctly. So in particular, what that means for induction is if I'm in a call by value language, I don't have to worry, it's just all fine, it works. But if I'm in a call by name language or something where there's delayed evaluation, we kind of have to be careful. If a program maybe loops forever or raises an exception, then there's a difference if I try to look at it and reduce it or not. And so if I try to apply induction in this call by name language where I care about the different things that might be raised or that it loops, I only can apply it in the case for equality. There's other propositions we might want to do, like for all and implies. But in the base case of two things being equal, I can apply induction if I'm actually using the x in a strict context. Then I can do induction on x, and I won't run into any problems, even if I'm in a weird call by name language with built-in effects. And well, you might not be as interested in that, but the other thing that does come up a lot is I might be doing coinduction, and if I'm in a call by name language, there's no problem, even if there's weird effects, which is a little bit odd. But if I'm in a call by value language, then we have to make sure that we don't apply the coinductive principle kind of whenever. We just need to make sure that, and this is the only sense of productivity that there is, that the programs return an actual value of some form, two values, to the output alpha. And essentially, if you're kind of wondering what this means, this is exactly the same thing as the normal restriction in the lambda calculus. If I'm in a call by value lambda calculus, I can only eta expand or reduce values, not general terms. So you're kind of familiar about that sort of thing. It's the exact same property that we do there, and this is the restriction that stops you from doing that. Right? So it's exactly the same nature there. And you also might be asking about, well, what about other reasoning principles? Maybe I really, really like bisimulation. What if I wanted to do that? So all of these kinds of other ways of structuring a coinductive proof are derivable. In particular, bisimulation is very popular. And you can derive that in terms of these axioms and these principles just as well. And the only caveat, it turns out, is that to do something like bisimulation or strong coinduction, it's the equivalent of strong induction, which means you assume the coinductive hypothesis for all possible smaller observations, not just the next one. You need the unrestricted call by name rule. But you don't need that for something like mutual coinduction. That works kind of whenever. that is my talk. I want to open it up for any questions you might have. Yeah. Maybe not. Yeah.
Yeah. Okay, so if you end up writing an implementation, you know Jasper Cox in Agda developer. So he's just got people that finished an internship with him that basically studied coinduction in Agda and compared the different methods. So there's a report that compares them. So if you have an implementation, that's a great way to see if it works or not in practice compared to what Agda supports. Yes. And Agda works mediumly. Yeah.
Thank you. I think it probably will work.
Yeah, and if you're not aware of it, there's a library for coinduction in Rock developed by Damien Plus and Yannick Zakowski. And it looks very similar in the ideas. They've never published a paper about it, but is your thing, I don't know to say this, like the math behind the plugin, because they've just written codes using lattices and stuff like that for coinduction. So are you actually providing a foundation for this kind of plugins they're doing?
Yeah, it might be from that sense. So I'm not familiar with that particular library, but a big part of the paper is kind of proving that this actually works, right? So this kind of theorem. So that might be what you're thinking, like the foundations that this is sound and kind of, well, I guess enough is implementing it and testing it in practice will be the interesting case there, yeah.
Well, actually, I'd like to see a slide.
Oh,
okay. Sorry.
Let me plug it.
Could you show the slide where you say like all observations on streams are either observations on the head or the tail?
Yes.
Because I was very confused by that.
There, that one maybe?
Yeah.
Yeah.
What if my observation is adding the first two elements of the stream? That involves both the head and the tail.
Yeah, of course. And this is kind of like the same thing of, saying that all numbers are successor or zero, but of course I might add two numbers, which isn't successor or zero, but it simplifies down to those. So for copying a stream and using both the head and the tail, it's saying we're copying it and we're running it 2 times with 2 different observations, right? And so that kind of has to do with those information effects that I said, duplicating some information and using it more than once.
Okay.
Yeah.
All right.
Yeah.